In the lead up to World War II, two German Nobel Prize winners by the name of Max von Laue and James Frank smuggled their solid gold Nobel Prizes out of the country. Von Laue was an outspoken critic of the Nazi Party, and Frank was of Jewish descent. Neither wanted their 23-karat gold medals falling into the hands of the Nazis. They sent them to Denmark, where they were safely stored at the Institute for Theoretical Physics of the University of Copenhagen. That was until the Nazis invaded Denmark in April 1940.
The German army rolled across the neutral borders of Little Denmark, and in a matter of hours it occupied the entire country. By nightfall, Denmark is erased as a nation, and the Danes go into slavery. Although only 6 months before, Hitler had announced, "We have concluded a non-aggression pact with Denmark. The Danes will not forget."
When the scientists at the institute heard about the Nazis marching towards Copenhagen, they quickly gathered for a meeting. They knew that if the Nazis were to discover the smuggled Nobel Prizes, many people, including von Laue and Frank, would face a severe and potentially lethal punishment. They frantically discussed what they should do with the medals. George de Hevesy, a Hungarian chemist, suggested burying them, but Niels Bohr, the famous physicist who ran the institute, said no. The Nazis would search everywhere. They would dig up the grounds. They would find them. Suddenly, de Hevesy had a better idea. He realized that he could use his chemical knowledge to hide the Nobel Prizes. Bohr gave him the green light, so de Hevesy went into his lab and made up a mixture of 1 part nitric acid to 3 parts hydrochloric acid, then dropped the Nobel Prizes in. Very gradually, the solid gold medals started to dissolve. It was a slow process, and by now they could hear the sound of Nazi boots marching down the street outside. If they were discovered, it could mean death. Let's take a look at the chemistry that was going on in that flask. First of all, gold is what's called a noble metal, meaning it's very unreactive, so the fact that it was dissolving in this solution is amazing in itself. Now, alone, neither nitric acid nor hydrochloric acid is able to dissolve gold, but together, that's where the magic happens. The mixture of the two has been known for centuries as aqua regia, which is Latin for royal water, so named because of its unrivaled ability to dissolve gold. Alchemists would have thought the breaking down of gold in this way was a key step in learning how to turn base metals into gold. With modern chemistry, we can understand how the mixture works. Nitric acid is an example of a strong oxidizing agent, which means it's very good at removing electrons from atoms. It's even able to do so with the very unreactive gold. The positive gold ions then dissolve and become a part of the liquid solution. However, when you drop gold into nitric acid without any hydrochloric acid present, this process doesn't just keep going until all the gold is dissolved, because the reaction is actually reversible. So the nitric acid will remove electrons from some of the gold atoms to give gold ions, but simultaneously, some of the gold ions will regain electrons to form gold atoms. This results in an equilibrium, which is tilted very far towards the side of normal metallic gold. In essence, only a small number of gold ions can exist in the solution at any one time. However, if hydrochloric acid is added, the chloride ions will react with any gold ions that form to produce tetrachloro gold ions, which then react with the H+ ions from the hydrochloric acid to give chloroauric acid. Now, because this process continually removes gold ions from the solution, this essentially allows room for the nitric acid to continue oxidizing the gold, supplying more and more gold ions to the solution, which are continually removed. This process can continue until the solid gold has fully dissolved. It was this reaction that de Hevesy was watching keenly as the Nazis approached the building. Finally, the gold dissolved completely, and he was left with an orange-red solution. He put the flask on a shelf next to some other chemicals, and minutes later, the Nazis burst in to search the building. In 1943, de Hevesy fled to Stockholm, and around this time he won his own Nobel Prize in chemistry for his work on radioactive traces. He remained in Stockholm until the end of the war. After VE Day, he returned to Copenhagen and went back to the institute. He walked into his lab and was relieved to find that the flask with the orange-red solution was completely untouched. He took it off the shelf and was now faced with the task of extracting the gold from the solution. He evaporated the excess aqua regia and decomposed the residual nitric acid by repeatedly heating the solution with additional hydrochloric acid. This converted the nitric acid into nitrosyl chloride, which could then further decompose into nitric oxide and elemental chlorine, both of which would boil away. This left him with solid chloroauric acid. To get metallic gold from this, he essentially needed to give electrons back to the gold ions. This process is called reduction. The chloroauric acid can be reduced by reacting it with a reducing agent such as sulfur dioxide. Sure enough, after the reaction, he was left with solid gold. De Hevesy sent the raw metal to the Swedish Academy in Stockholm. The gold was recast into 2 Nobel Prize medals that were then presented back to von Laue and Frank at reward ceremonies in 1952. The gold had been right under the Nazis' noses for the entire war and they had no idea. What a brilliant use of chemistry. Let me know in the comments of any other brilliant uses of chemistry throughout history, and if you enjoyed this video, I'd really appreciate if you considered subscribing. It really helps out the channel. Thanks for watching, and I'll see you in the next one.